Let's dive into one of the most fundamental forces in the entire universe. It's this invisible glue, really, that holds galaxies together, it keeps planets locked in their orbits, and it's what's planting your feet firmly on the ground right now. We're talking about the profound, ever-present force of gravitation.
I mean, seriously, have you ever just stopped and thought about that? We've got this massive rock, the moon, just hanging out up there, constantly circling us without flying off into space. At the exact same time, you, me, everything, we're all stuck to the surface of the Earth. You'd think those are two completely different problems, right? Well, it turns out the answer to both is the exact same, and it is beautifully simple.
And here it is, the universal law of gravitation. Okay, that sounds a bit wordy, but what it really boils down to is two simple things. First, the more stuff an object has, the more massive it is, the stronger it pulls on other things. And second, that pull gets weaker, really fast, the farther apart things get. This isn't just about planets and moons, by the way. You have a tiny gravitational pull on the phone in your hand, and believe it or not, it's pulling right back. It's this universal dance of attraction.
Now, calling this law universal is no exaggeration at all. This one single, elegant idea connected all these phenomena that for centuries seemed totally unrelated. It was like finding the master key that unlocks some of the biggest mysteries of the cosmos.
And this is just how powerful it is. The very same law explains why an apple falls from a tree, why the moon orbits the Earth, why all the planets go around the sun, and even why we have ocean tides, which are just the moon and the sun pulling on our oceans. Before this, nobody thought these things had anything to do with each other. This law tied it all together.
So here's this number, the gravitational constant, or big G. And that tiny little 10 to the minus 11 tells you something huge. It means that on a human scale, gravity is actually an incredibly weak force. It's the reason you don't feel the gravitational pull of your coffee mug. The force is there, for sure, but you really need something with the insane mass of a planet for it to become a force you can actually feel.
And that brings us to something we all talk about every single day. We tend to use the words mass and weight like they're the same thing, but in the world of physics, they couldn't be more different. And gravity, well, gravity is the key to understanding why.
Okay, let's break this down. Your mass is the actual amount of stuff you are made of. Your atoms, your molecules, all of it. And that is constant. Your mass is the same here on Earth as it would be on the moon or just floating around in deep space. Your weight, on the other hand, is nothing more than the force of gravity pulling on that mass. So because gravity is different in different places, your weight changes too.
This is the perfect example, right? The moon has way less mass than the Earth, so its gravitational pull is a lot weaker. How much weaker? It's about 1/6 as strong. So while the amount of you, your mass, wouldn't change one bit, you'd only weigh about 1/6 of what you do on Earth. You could jump 6 times higher. So we've got weight, this force that's always pulling us down, but the effect of that force can change in a huge way depending on how it's actually applied. This leads us straight into the super important ideas of thrust and pressure.
Let's just do a quick thought experiment. Picture yourself on a beach, standing on some loose, dry sand. It's pretty obvious what happens, right? The force of your body's weight pushes down, and your feet just sink right in. Simple enough.
Okay, but now what happens if you lie down on that exact same patch of sand? You don't really sink in much at all, maybe just a tiny bit. But hang on a second. Your weight, the force pulling you down, is exactly the same. So what changed? What's the secret?
The answer starts with something called thrust. Now, thrust is just a fancy name for a force that acts straight down, perpendicular to a surface. In our beach example, your weight is the thrust. So whether you're standing up or lying flat, the total thrust pushing down on the sand is identical. So the real key to the whole puzzle is pressure. See, pressure is that thrust divided by the area it's pushing on. When you're standing, all of your weight is focused on the tiny little area of your feet. That creates really high pressure and it pushes the sand away. But when you lie down, you spread that exact same force over the much larger area of your entire body. Less pressure means you don't sink. Simple as that.
All right, so now that we've got a handle on how gravity pulls things down and creates pressure, let's flip the script and talk about the counterforce, the amazing phenomenon that pushes things up. This brings us to the science of floating.
This is a classic physics puzzle, and it's a good one. We all know that steel is way denser than water.
If you drop a solid chunk of steel into a lake, it sinks like a rock, no question. And yet, we build these gigantic ships out of thousands and thousands of tons of steel, and they just bob around on the ocean like it's nothing. How is that even possible? Gravity is yanking down on all that steel, so what in the world is pushing up?
The answer has a name: buoyancy. It's this upward force that any object experiences when it's placed in a fluid, and that could be a liquid like water or even a gas like air. It's basically a constant battle. Gravity is trying to pull everything down, and buoyancy's always pushing up.
So, who wins this epic tug of war? Well, it all comes down to a little thing called density. If an object is, on average, denser than the fluid it's sitting in, gravity's downward pull is going to be stronger, and it sinks. But if the object's average density is less than the fluid's, that upward buoyant force wins the fight, and it floats.
Now, this whole relationship between weight and buoyancy and density, it wasn't really understood for thousands of years. That is, until one of history's greatest thinkers had a legendary eureka moment. So let's take a look at Archimedes' big idea.
And this is just pure genius. The buoyant force that's pushing up on an object is precisely equal to the weight of the fluid that the object pushes out of the way. So think back to our giant steel ship. It floats because its massive, hollow shape pushes a huge volume of water aside, and the weight of all that displaced water is way greater than the weight of the ship itself. That creates a massive upward force that keeps the whole thing afloat.
And this isn't just some dusty ancient idea from a textbook. We use Archimedes' principle all the time. It's obviously fundamental to designing ships and submarines, but it's also the science behind things like lactometers, which check the density and therefore the purity of milk, and hydrometers, which are used to measure the density of all sorts of liquids.
So, from the orbit of the moon all the way down to a ship floating in a harbor, it all connects back to these amazing fundamental forces: gravity, pressure, and buoyancy. They are acting on you and everything around you right this very second. So the question is, what else in your world can these incredible principles explain?